You've probably seen these strange little drawings before, right? For decades, physicists have been using them to make the most accurate predictions in the entire history of science. But they've been hiding a secret, a really profound truth about how reality itself works. So today, we're going to pull back the curtain on that secret. And it all starts by asking a very simple question. What are these things actually for?
Okay, so what you're looking at are Feynman diagrams. Now, on the surface, they look like simple cartoons, particles coming in, bouncing off each other, and going out. And for the longest time, that's pretty much how everyone saw them, like a kind of magic trick that just happened to work. It solved a huge crisis where all the other calculations were just spitting out nonsense infinities. But the big question never really went away. Why do they work so perfectly? What are they really calculating?
And right there, that's the heart of the mystery. I mean, the gap between what these diagrams look like and what they truly are, it's just massive. They are not just little pictures of collisions. They are kind of shorthand for one of the deepest ideas in all of physics, a calculation of probability that is based on pure geometric distance. It's a completely different way of thinking about reality.
So how do we get from A to B? How do we connect the simple picture to this deep geometric idea? Well, it all comes down to a single, incredibly powerful formula. You can think of it like the Rosetta Stone for quantum field theory. It's the key that unlocks everything.
Okay, here it is. And I know, it looks a little intimidating, but don't worry about the symbols just yet. This is the master equation. It kind of looks like a bell curve you'd see in a stats class, right? But what it's describing is, well, it's absolutely profound. It's telling us that the probability of something happening, p of x, depends exponentially on the square of a distance, d squared. So let's break down what that really means.
All we have to do to get this is just translate what these symbols actually mean for the universe. Okay, first up, x. This isn't just a point in space. Now, this is an entire state of the universe's fields. Think of it like a complete snapshot of everything at one instant. Then you've got d squared. Physicists call this the action, but really it's just a way to measure how far that snapshot is from the most efficient, perfect classical path. And t? That's just Planck's constant. It's the number that basically turns the quantum world on. So here's the bottom line. The more a state wanders off from that perfect classical path, the exponentially less likely it is to ever happen. Simple as that.
Now, to really wrap your head around this, we need to picture a new kind of landscape. And I'm not talking about hills and valleys. I'm talking about a vast abstract space where every single possible state of the universe is a single point.
This amazing landscape is called configuration space. And yeah, it's a truly mind-bending idea. I mean, try to imagine a space with an infinite number of dimensions, where every single point isn't a place, but an entire possible version of our universe. A point right here could be our universe, but with one electron shifted a tiny bit to the left. A point way, way over there could be a universe where stars never even formed. They all exist as possibilities in this space.
So, in this vast landscape, the classical world, the reality we see every day, that's like the perfect straight-line path at the very bottom of a valley. It's the single most efficient route from A to B, the path of least action. But here's the thing about quantum mechanics. It's different. It doesn't just stick to that easy path. Nope. It actually considers every single path you could possibly imagine, every detour, every wrong turn, every scenic route, and it adds them all up. And each path is weighted by exactly how far it strayed from that perfect classical path.
And that's what a Feynman diagram really is. It's a map of one specific journey through the space of possibilities. Let's take a look at a simple interaction. We start with two electrons. That's our initial point in configuration space. Then we deviate. One electron spits out a photon, changing the state of the universe just a little bit. That's a step away from the straight path. Then the other electron absorbs that photon, another change. And finally, we end up in our final state with two electrons again. The diagram is just a simple sketch of one of these detours.
Okay, so what about the lines in the drawing? These lines, which physicists call propagators, they are not just random squiggles. The actual math that defines them is our master equation. That line literally calculates the geometric probability, our old friend exp pi d squared over 2t, for a particle to travel between 2 points. It's a direct measure of likelihood spreading out across the landscape.
And those points where the lines meet up, the vertices, those are the interactions. They're the moments the journey takes a turn and deviates from a simple straight-line path.
So the more vertices a diagram has, the more complicated the path, the more twists and turns it takes, and every vertex you add makes the whole journey a little bit more unlikely, a little bit further from that perfect classical path.
You know, this whole geometric way of looking at things, it doesn't just make it easier to understand. It actually solves some of the biggest, most nagging headaches in all of quantum physics, from phantom particles to those pesky infinities that got us started.
All right, let's tackle a big one, virtual particles. You've probably heard the pop science version, right? That there are these little particles that pop in and out of existence, breaking all the rules for a split second. Well, this geometric picture gives us a much cleaner, much more sensible answer. They aren't real particles at all. They're just mathematical placeholders for the waypoints on a journey through configuration space. The journey itself is real, but the waypoints are just part of how we do the math.
Okay, but let's circle back. What about that original problem Feynman was trying to solve? Remember those calculations that just kept spitting out infinity over and over again? Where did they come from, and how on earth does geometry fix that? The geometric answer is actually surprisingly simple. Those pesky infinities, they came from looking at paths in our landscape that were way, way too short. We're talking about impossibly tight turns, twisting in on themselves at scales so small they don't make physical sense. So how did physicists deal with this? With a really clever process called renormalization.
Renormalization is actually built on a really common sense idea. Basically, the physics we can measure out here at our scale shouldn't depend on what's happening at some unknowable, infinitely small scale we can't see. So what we do is set a cutoff. We just decide to ignore any paths that are too short, that twist around too much. Then we cleverly adjust our measurements to account for the total effect of all those tiny quantum detours happening under the hood. It's kind of like recalibrating your GPS to account for all the little bumps and imperfections in the road that aren't on the map.
So, okay, we have this beautiful, super elegant theory. It reframes quantum mechanics as a geometry of possibilities. But is it true? I mean, is there any hard proof that the universe actually operates this way? Well, the answer to that comes from what is, no joke, one of the most stunning achievements in the entire history of science.
The ultimate test was to calculate one very specific property of the electron, its magnetic moment, which is really just a fancy way of saying how strongly it acts like a tiny little magnet. The great thing is, this is a property we can go into a lab and measure with unbelievable precision.
So using this whole geometric framework, summing up all the different paths through configuration space, physicists calculated a theoretical value. And when they compared that calculation to what they measured in the lab, the numbers matched to 12 decimal places. Just let that sink in. 12.
I mean, just look at these numbers side by side. It is literally impossible to overstate how mind-blowing this is. That's like measuring the distance from LA to New York City and being accurate to within the width of a human hair. This isn't just a good theory. This is, flat out, the most precisely tested prediction in the history of all science.
An agreement like that, it's not a fluke, it's not a coincidence, it's about as powerful a confirmation as you can get that this whole geometric picture is fundamentally correct. It really truly seems that at the deepest level we can probe, reality computes probability based on geometric distance in this vast space of possibilities.
And so that leaves us with this one, final, incredibly powerful idea to chew on. So forget about thinking of particles as little billiard balls bouncing off each other. Instead, picture this. Particles interact by exchanging pure geometric probability with each other across an infinite landscape of everything that could possibly be. And that is the secret that Feynman's weird little drawings have been telling us all along.